while we're discussing solar days and the Earth's orbital motion, there are two other small imprecisions in what I said that I need to correct. One is, I said that 24 hours are adjusted to be a mean solar day, and you can ask, what's so mean about a solar day? This was mean in the sense of average. It turns out that solar days are not all the same length. Why is this? Well, the Earth's rotation about its axis is extremely uniform. We'll talk later about how it fails to be uniform, but it's almost exactly uniform, certainly on the levels of precision that we're talking here. So the length of a sidereal day is very constant. The length of a solar day is not. Remember, the difference between a sidereal day and a solar day is associated to the sun's motion along the celestial sphere. The sun moves to the east by 4 minutes every day, and therefore there is a 4-minute difference between solar and sidereal days. But the sun's motion to the east along the celestial sphere is not uniform. So the first cause of this is that the sun moves uniformly. If the Earth orbits the sun uniformly, then the sun would move uniformly around the Earth, but it would move along this tilted path of the ecliptic. What this means is that near the equinoxes, the sun's motion is not parallel to the celestial equator. It's not purely in right ascension, it's also changing declination. Whereas near the solstices, the sun's motion is parallel at the maximum and minimum. The sun's motion is now parallel to the celestial equator, and so its motion in right ascension is slower near the equinoxes and faster near the solstices, and the 4 minutes is an average. And that is one reason why the length of solar days is not uniform. There's another correction to this. In fact, the rate at which the Earth orbits the sun, or equivalently the sun orbits the Earth, is not precisely uniform even along the ecliptic. This is because the Earth's orbit is not precisely circular, and the Earth is in fact very slightly nearer the sun in January than it is at any other time of the year. At that time, the sun's apparent motion in the sky is fastest, and 12 months later, it is slowest, and so even along the ecliptic, the sun's motion is not precisely uniform. Moreover, I kept talking about the fact that the Earth's North Pole maintains its orientation in space as the Earth orbits, so that it always points in this direction of the celestial North Pole, where sits some particular star, say the pole star. And this, it turns out, is also inaccurate. We are building up more and more precision into our model, and in fact, the Earth is spinning about its axis. It's acted upon, as we will see, by the sun and the moon applying tidal forces, and like a spinning top spinning on a table and acted upon by gravity, the Earth's axis wobbles in the same way that a spinning top wobbles, except it's a little bit tricky. A spinning top will wobble in the same sense in which it is spinning. The Earth's polar axis actually wobbles in the opposite sense to the sense it rotates. In other words, the celestial North Pole moves to the west along the celestial sphere. So the Earth's North Pole does not always point in the same direction as I've been saying so far. Instead, it's tilted by 23.5 degrees to the orbit, but as the Earth rotates to the east, the celestial pole very slowly wobbles in a big circle in the sky of radius 23.5 degrees about the perpendicular to the orbit. And this wobble, called the precession, takes about 26,000 years. What that means is that the point that we define as the celestial North Pole moves with time. And what this means is that what we now call the pole star will in a few thousand years no longer be the pole star. The Earth's North Pole will face in a different direction. More intriguingly, the celestial equator changes. As the Earth wobbles, the tilt of the celestial equator relative to the orbit, or of the ecliptic relative to the celestial equator, is always 23.5 degrees, but at different orientations. What this means is that the equinoxes, the hinges at which, the points at which these two circles are hinged, move around the celestial equator. Hence, this whole wobble leads to what is called the precession of the equinoxes. If the vernal equinox shifts, then the coordinates of all stars shift because the origin, the intersection of the equator with the meridian including the vernal equinox, moves. And so the coordinates of a given star change. This is most clear if you think about it. The star, which now has celestial coordinates declination 90 north, which is the North Star, will not have those same coordinates for very long as the Earth continues to wobble. And so when you look at right ascension and declination for a given star, they will be given in terms of some epoch, most typically epoch J2000. That means these coordinates are given relative to the position of the celestial equator and the vernal equinox as of the orbital parameters on January 1, 2000. Back in Athens, it's still November 27th. What I've done is I've attempted to have the software keep us centered on the North Celestial Pole so that we will be following the North Celestial Pole as time goes on, and I will make time move by centuries. And what you will notice is that over time, the celestial pole moves. The celestial pole started out very near this pole star of Polaris, and the celestial pole moves, and it moves in this great big circle in the sky, so that by the time you get to 10,000 or 11,000 AD, Vega is closer to being a pole star, and of course in 26,000 years, the pole star the celestial pole will have completed its wobble, and we will again have Polaris as a good North Star. Let's try to see that again, and at this point, we should pay attention to the position of the vernal equinox. Of course, as the pole star moves, so too does the vernal equinox. Remember that it is currently in the constellation of Pisces. You can see that it's moved quite a distance along the equator. Remember, it completes a full circuit of the equator, and over this time, and I'm now dialing time back to the present, and the vernal equinox is moving to the east along the celestial equator, and as we approach the present, we find that around the present, 1,000 years ago, the vernal equinox is indeed in the constellation Pisces, and as you move time forward, you will see that on or about 2600 AD, the vernal equinox leaves the constellation of Pisces and enters the constellation of Aquarius. That means we are currently living in what is called the Age of Pisces, and as of 2600 and some, we will be in the Age of Aquarius. If you look at 22,000 BC or so, the time that pyramids in Egypt were being constructed, the North Star that we use today was nowhere near the North Celestial Pole, and in fact, dating of pyramids is based to some extent on astronomical conjectures of what it was the Egyptians used as a North Pole, and there's real information to be gleaned from this wobble of the Earth's pole. We started out trying to understand which stars were going to be visible when. This was in itself enriching. Along the way, we figured out the reasons for the seasons, and we started investigating the sort of arcane phenomenon of the wobble of the Earth's axis and the precession of the equinoxes, and came up with an understanding of ways to date Egyptian pyramids based on which North Star they align to. So we're making progress in understanding the moving parts of this model of the universe that we're constructing. The most conspicuous absence is the moon, and it is to that we turn next.